Bon, quelques mots en français. Donc, depuis que Monique Tonat est repartie ce matin vers la Côte d'Azur, je suis sûr que je suis le plus... celui qui connaît... Je suis... Bon, le plus âgé, c'est autre chose, ça. Mais je suis celui qui connaît Denis depuis le plus longtemps. Et en fait, depuis 44 ans. Hein? Donc, j'ai compté, j'ai vérifié avec Denis. Donc, il a suivi mon premier cours de... C'était pas tout à fait le premier, enfin disons si, première année où j'étais en poste à Marseille, j'ai fait un cours de DEA qui parlait de chaînes de Markov qui convergeaient vers des diffusions, de d'EDP associés et de convergence de schémas numériques, donc il y avait de l'analyse numérique des EDP, des processus stochastiques. Et du coup, Denis qui a décidé de faire son mémoire avec moi, son mémoire ça s'appelait DEA à l'époque, hein, ben, je me suis dit, tiens, pour l'instant, je ne vois pas trop de travaux sur l'analyse numérique des équations différentielles stochastiques, donc pourquoi pas. Et voilà, et ça a été le début d'une longue histoire parce que, donc, ce que je veux dire, c'est que ce qui m'impressionne dans la carrière de Denis, c'est qu'il a tenu, sous toute la durée, il a tenu ce sujet, cette thématique, pas de façon étroite, il a fait des tas de choses qui étaient liées à ça, hein, il ne s'est pas limité à ça, mais il n'a jamais abandonné ce sujet, et je pense qu'il a eu raison, parce que c'est quelque chose de riche, d'important, et qu'il a su très bien développer, seul ou avec des collaborateurs ou avec des étudiants. Donc je crois que cette ténacité a payé. Donc bravo Denis. Bien, alors moi, là c'est pas de la ténacité parce que les modèles des épidémies, je ne sais pas depuis combien de temps j'en fais, mais ce que je vais raconter là, c'est des choses où vous allez voir, donc c'est des modèles non markoviens, un petit peu qui sortent des modèles classiques. Et ça, j'ai commencé en janvier 2020, très précisément, avec Go Dongpang, que j'avais rencontré en juillet 2019 à une conférence aux États-Unis, donc juste avant l'épidémie de Covid. Donc ce travail est un peu indépendant de l'épidémie de Covid, mais bon, il y a eu un petit peu d'interaction, vous verrez. Bien. Donc, le travail est en collaboration principalement avec Go Dongpang, une grosse partie aussi avec Raphaël Forien, et la dernière partie avec Arsène Brice-Zotza, qui est étudiant en thèse à AMU, aix-marseille Université. Bien. Donc, sorry, I should switch to English. So, in almost 100 years ago, Kermack and Kendrick published a paper which proposed SIR, so S like susceptible, I like infected, R like recovered model. So a compartment model with 3 compartments, propagation of epidemic diseases. And in their model, they have an infection age-dependent infectivity, an infection age-dependent recovery rate. They also treated the particular case, a special case of constant infectivity and constant recovery rate. And that paper was quoted, according to what I saw on the internet, almost 11,000 times. But almost all successors, they consider only the simple ODE model, which you get only in the case of constant rates. So dsdt equals minus lambda si, didt equals lambda si minus rho I, drdt equals rho I. So where S denotes the number of susceptible individuals, I is the number of infected individuals, and R the number of recovered individuals. Well, a bit later it will not be numbers but proportions. Anyway, usually people refer to this as numbers, but how can a function values in n be the solution of an ODE? I mean, it's impossible. Okay, so the general model of Kermack-Kendrick with non-constant rates involves rather an integral equation of Volterra type, or a PDE, as we will see. Okay, so constant versus non-constant recovery rate. So if I denote the length of the infectious period, Okay, if we have a constant rate mu, that is p of I larger than t is e to minus mu t for all t, that means that I, of course, follows the exponential distribution of parameter mu. However, if mu of t is measurable from R plus into itself with infinite integral, and we assume that probability that I is larger than t is e to the minus integral from 0 to t of mu of s ds, then it is easy to deduce that I has a density mu of t e to the minus integral from 0 to t of mu of s ds. Conversely, given the density f on R plus, we define the hazard function as mu equal to f of t divided by integral from t to infinity of f of s ds. Then we have this situation. Okay, so if we assume that the individuals recover at an infection age-dependent rate and not a fixed rate, as is usually done in the literature, this allows to choose an arbitrary distribution with density. In fact, we will not need density, arbitrary distribution. Okay, quickly, of course, everybody knows what is the standard Poisson process. So if P is standard Poisson process, then P of lambda t is a rate lambda Poisson process, and P of integral from 0 to t of lambda of s ds is a rate lambda of t varying rate Poisson process. And it's in fact more convenient to rewrite such a lambda of t Poisson process as a double integral u less than lambda of s of q of ds du, where q is a standard Poisson random measure on R2 plus. Standard Poisson random measure means that the mean measure is a Lebesgue measure. And so as it is written, it's a sum of Dirac measures at random points, blah, 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 blah. You probably know all that. And finally, the law of large number, it is well known that 1 over np of nt tends to t almost surely as n goes to infinity. But this is locally uniform in t as follows very easily from Dini's second theorem. Okay, if you don't know Dini's theorem, when I say that many people don't know what is Dini's theorem, you just go to Wikipedia and you find the proof. It's an easy exercise that everybody can do. Okay, so now let's quickly go through the case of the Markov model. So assume that the population, I assume here for simplicity no demography. Of course I could edit, but so the total population size is fixed over time, it's capital N. So number of susceptible plus number of infected plus number of recovered is constant. Suppose that each infectious individual meets other at rate beta, and with probability the proportion of susceptibles in the population, and that probability is the proportion of susceptible individuals, then the individual who is met is susceptible, in which case the encounter results in a new infection with probability p. And now I define lambda to be beta times p, and then if I assume that the durations of the infectious periods of the various individuals are IID with the law exponential of mu, then the evolution of Sn of t, In of t, Rn of t is exactly like this, where P-inf and P-rec are two independent standard Poisson processes. Then I divide these by n, and just using the law of large numbers I have given for the Poisson processes, it is rather immediate that the proportions converge as n goes to infinity almost surely to the solution of this system of ODEs, which I have shown on the first slide. Okay? So good, so well. But now let's go back to the general model of Kermack-McKendrick. First, you have a fixed infectivity during an infectious period of length I, and I want the infectious period to have an arbitrary distribution. So I just give myself the distribution function capital F of t. Now the infection age recovery rate is the hazard function of I, which is little f divided by O. Okay, Fc of t is always 1 minus f of t. It's a notation which I use all the time. And okay, so I have this situation, but I don't need to assume infected density. Then the stochastic model is not Markov unless f is the exponential distribution, i.e. unless mu is constant. And as n goes to infinity, now I have as limit a system of Volterra integral equations. Of course, the first equation is an ODE, but you see that the two next equations are Volterra equations. Okay? And the approximating thing is not Markov, and this has memory. This system of equations have memory. In fact, of course, you solve the two first the system given by the two first equations, and then once this is solved, of course, there is a unique solution, very easy. Then you compute R bar given by the last formula. Okay, and there is a central limit theorem. I don't want to discuss this because I don't have time, but just to say that we each time we prove all over the numbers, then we prove central limit theorem. It may take months or maybe years to prove it, but we do it. Okay, now, okay, this is COVID in France in the year 2020. And okay, the very irregular dashed line is the number of recorded hospital deaths every day or every day. Now, our model with memory, if we adjust, we can adjust the coefficients so that the model with memory gives this. Okay? Now here, oops, the most important thing is that this is the time of the start of the lockdown. Okay? So after the lockdown, of course, the rate of contact between people changes dramatically, very quickly, instantaneously, so to speak. And okay, now, of course, so you see that the true epidemic has memory. Of course, hospital deaths during those days, of course, depend upon how many were infected before lockdown. And now our system with memory can adjust very easily to the data, while the Markov model, there is a jump in the derivative here. Of course, those who use Markov models to model the COVID, they will just, okay, maybe I'm a bit nasty, but I would say they will cheat, because you know, because the lambda changes drastically, jumps from one value to another, you have this jump in the derivative. But of course, what you can cheat and have lambda decrease continuously, slowly with time, and then you can adjust to the data. But I don't think this corresponds really to what happens in reality. Okay, now, okay, maybe I skip this. I mean, this is just the infectivity. This was a paper published by Chinese medical doctors in 2020, which shows the evolution of the infectivity of patients. Okay, so as Kermack-McKendrick proposed in their seminal paper, 1927, and as I showed you, it seems the case for the COVID, the infectivity depends upon the time elapsed since infection. Depends upon the age of infection of each individual. So let lambda be a random function with non-negative values. So maybe the lambda is first 0 during a so-called exposed period, latency period. I have not talked about that so far, but I introduce that now. And then this is duration during which lambda is oops, okay, this is not well written, but anyway. I is the duration during which, length of time during which lambda is strictly positive. And, okay, so I is the infectious period. We assume that to each individual is attached a copy lambda I of that random function, where the lambda I are IID. And to the initially infected individuals, we attach as a type of function lambda 0 j of t. So we request that lambda belongs almost surely to the scored space D, and that the sup of lambda is less than a fixed constant lambda star. Unfortunately, I would love to be able to treat the case where this is not a fixed constant, but it's a random variable which has some finite moment, but we are not able to do that so far. Then one can establish a law of large numbers as n goes to infinity of the corresponding individual base model. Now we need to define the total force of infection in the population. So this is the total force of infection at time t of those initially infected, who were infected at time 0. And these, okay, n of t counts the number of individuals who are infected on the interval 0t, and the tau and I are the successive times of infection after time 0. So this is the total force of infection of those infected between time 0 and time t. And in red, you see in the case where lambda doesn't depend upon t, but is fixed, is a fixed constant, this is just lambda times the number of infectious individuals. So in that case, we don't need to define that process Fn of t, that force of infection. Okay, then I denote as before Sn, In, Rn, the number of susceptible infected recovered individuals in the population. The sum of those three is constant equal to n. Bar n denotes 1 over n the quantity, same with I and R and with F. And then those four converge to a limit in probability as n goes to infinity, and the convergence is for the topology of the space D, and where if lambda bar denotes the expectation, lambda bar of t denotes the expectation of lambda of t, lambda bar 0 of t is the expectation of lambda 0 of t, and capital F is a distribution function of E plus I. The time between the time of infection until the time when eventually lambda is 0 forever, okay? Then we have this system of integral equations. Again, you just need to solve the system composed of the two first equations. Once this is solved, and therefore, of course, it has a unique solution, then you get an explicit formula for the two last quantities. Okay? So, now the problem here is that there is a difficulty with, okay, the typical proof you had in mind first, and which we used in the first paper on this result, which appeared in SciAm Journal of Applied Maths in 2021. The problem is, okay, we show that each quantity is tight in D, and then we take a converging subsequence, and all converging subsequences have the same limit, and this limit is deterministic, so we have convergence probability of the whole sequence. But there is a difficulty with the tightness in D of this guy if we don't assume more assumptions on lambda. And in fact, if you accept to have convergence in D of the first and the two last, I mean, everything except Fn, F bar n, converge in D, F bar n just converges pointwise for each t, then this kind of argument I was just sketching is going to work with the assumptions I was giving. However, okay, and I wanted to say that this is compatible with this is exactly the equations in the 1927 paper of Carmack-McKendrick. But if we want to, but finally we found a proof for the convergence in D to the power 4 without more assumption on lambda, we were inspired by the work of Chevalier, student of François Delarue, and the idea is to compare 1 over n an of t with 1 over n the sum of aj of t, where aj of t is, so to speak, almost it is 0 until the individual j gets infected, and it's 1 once this guy is infected. Now this is an IID sequence whose law is the same as this, where you see this is sort of SDE, but you see that tau is a jump time of A, so the coefficient of the SDE depends upon the whole law of the solution. And this is a type of Makin-Vlasov equation, so to speak. Okay, so using, the idea is that if you compare this quantity with this, you can show that the difference goes to 0, and now this is a mean of IID elements of D, so the usual law of large number works, and you don't need anymore any additional assumption, you get the convergence in D. Okay, so that was just one short. Now, alternative description. So far I was saying, okay, my model with memory, my limiting deterministic model of the non-Markov stochastic model with memory is a system of integral equations. But you know, when you have a non-Markov process, often if you increase the dimension of the process, you can make it Markov. And in fact, you can always, if you increase the whole path in the state, so that is, you transform it into an infinite dimensional process, it becomes Markov trivially. And that's essentially what we do here. So now, instead of writing integral equations, we can write PDEs. What we do is that we introduce as a new variable the age of infection explicitly in the model. Now we define Jn of Ta as the number of infected individuals at time t who have been infected for a duration less than or equal to A. Then I renormalize this by n, and one can show that as n goes to infinity, this J bar n of Ta converges to J bar of Ta in probability locally uniformly in T and A, where we have J bar of Ta equals, okay, the contribution of the initially infected individuals plus the contribution of the newly infected individuals after time t. Now, of course, here we need an assumption on this initial condition. That is, we need to specify when those who were infected at time 0, they have been infected in the past. So we have to assume a law of the time when they were infected in the past. Okay, now suppose that f is absolutely continuous with f prime equals little f, and that this initial condition is also absolutely continuous with density I bar of 0a. Then for all t, this J bar t of dA is absolutely continuous, and its density satisfies the following first order PDE. So dA dt plus di dt, plus di dA equals minus mu of A I of Ta, where again mu is the hazard function of associated to capital F. The initial condition is just the derivative of that quantity, and the boundary condition at the boundary, on the boundary A equals 0 satisfies this identity. Okay, you see that there is no problem of memory here. Everything is at time t, okay? But of course, we have gone to infinite dimension. Now, of course, it's obvious that what is little I bar of t0, derivative of at age of infection 0 of capital J of T bar J of TA. This is just the flux of new infected individuals. So this is minus S bar prime of T. Okay? And in fact, it is easy to write an integral equation for I of T0. Okay, maybe I write it. I didn't put it on the slide. Maybe I can write it on the board. It's just from this, it's obvious that it's this minus integral from 0 to t of I bar of S0 ds. So the initially susceptible minus those who have been infected between 0 and t. So this is the same as S bar of t, in fact, times integral from 0 to infinity of lambda bar y plus t I bar of 0 y dy plus integral from 0 to t of lambda bar of t minus s I bar of S0 ds. Okay, and it is easy to show that this Volterra equation has a unique solution, and then it is easy to show that any solution of that PDE is easily expressed explicitly in terms of the initial condition and the boundary condition. So this gives the existence uniqueness of the PDE. Okay, now a word about the time of extinction of an epidemic. So this is work with different co-authors as the rest, with Ibrahim Adrame and Anicet Mugabe-Porcor. Suppose we are in a situation where starting from t equals t0, an epidemic is declining. That is, the mean number of infects, my R, I don't write it R0 because R0 usually at the beginning of the epidemic. So my R effective is less than 1, while the total number of infected individuals is, let's say, capital M, which is much less, a smaller order than capital N, the size of the population. Then deterministic models are no longer valid because the proportion of infected individuals is 0. Okay. The epidemic is well approximated by a subcritical branching process, which decays essentially like an exponential e to the minus rho t minus t0. This last part of the sentence is proved in the Siam paper. Now, the approximating branching process associated to our varying infectivity model is a non-Markov continuous time branching process. And we have been able to derive an equation for the distribution function of the time of extinction, given that a unique infected individual got infected at time t0. And then you say it's not unique, there are more, and they have been infected before time 0. So once you have this quantity, you can compute what you are interested in. Now, the important thing that we notice that in the case of the Markov SIR model, there is an explicit formula for the distribution function of the time of extinction. And if we compare our model with a Markov SIR model with the same R effective and the same rho, then we see that the Markov model underestimates the time of extinction. That is, if you think that the reason why R effective is less than 1 is due to the fact that people are forced to wear masks, or that some movements of population are limited, then there is a danger that using Markov's SIR model, maybe those measures are not enforced long enough. Okay? Next, now let me turn to my last topic, which is now not only varying effectivity, but varying immunity or susceptibility. Okay, in almost all models in the literature, the immunity jumps, so far I've considered so-called SIR model. So susceptible, infected, recovered, and that's the end. Now let me switch to SIRS. That is susceptible, infected, recovered, and then again susceptible. So people lose their immunity. You know that in the COVID, for instance, that is the case. The immunity doesn't last very long. So you have to consider such kind of models. Of course, there are those who die in the meantime, but I don't go into too much. Maybe those who die, they just stay forever in the R compartment. R can include the dead, it's no problem. They don't contribute to the continuation of the epidemic, of course. Now, this, so as I said, jumping from the R compartment into S compartment, that is, here you are fully immune, here you are fully susceptible. It's completely unrealistic to think that there is this sudden jump. You don't jump suddenly from full immunity to zero immunity and full susceptibility. That's not the case. It's well known for the COVID that it's not the case, of course. And the fact that immunity is waning gradually, this was already discussed in the 1932 paper of Carmack-McKendrick. They have also another paper the next year, 1933. Okay. Now let me state our model for this situation. Now K now is an index for a given individual. So Sk of t is a susceptibility at time t of the case individual. The total susceptibility is, of course, the sum of all those Sk of t. Okay? No doubt. If someone gets infected at time t, the probability that K is chosen is this probability equals Sk of t divided by the total susceptibility. Okay, that's quite natural to assume that. Now we assume that the ith infected individual after time 0 has at time t the susceptibility. Okay, this is tau ni is the time of infection of that guy. Okay, so t minus tau ni is the time elapsed since infection or the age of infection at time t of that individual. So he or she has that susceptibility at time t. While the jth individual who was infected at time 0 has at time t the susceptibility gamma 0 j of t, where the gamma I are IID 0, 1 valued random functions, which are non-decreasing. We don't need absolutely to assume that, but it's quite natural, and satisfy that gamma I of t is 0 if t is less than the end of the immunity period, or the length of the immunity period. I should say, not the end, the length. Okay, so let me explain on the picture. So I consider one individual. This is the time of infection. So you get infected at time 0. First, probably you are exposed. You are not yet infectious. It's a latency period. Then your infectivity increases up to a maximum and then decreases. Then you are immune. You are no infectivity 0, but susceptibility 0. And then your susceptibility starts to raise up to a limit, which here I've taken to be 1, but could be less than 1. And in fact, okay, this is ongoing project now. We could, of course, have this limit depend upon the number of previous infections. Okay, so of course, I insist that lambda and gamma cannot be non-zero at the same time, both non-zero at the same time. Okay, one of them is always one of them, at least one of them is zero. Okay, so now this is the total susceptibility in the population. This is the total force of infection in the population. This is the number of new infections between 0 and t. Okay, so first, those who were initially infected, they have a susceptibility which is gamma 0 k of t. It's first 0, but after some time it increases. But this is until a new infection. Okay? As soon as your susceptibility is non-zero, you may be infected or reinfected. Okay? This is very important. I mean, the huge difference between those two formulas are those indicator functions. Okay, and here, maybe it's here you see you're at time t, that the guy number Mr. I has been infected at time t and I. So at time t minus t and I, its susceptibility is gamma I of t minus tau and I. But until the person is reinfected. Okay? And the fact that you have these indicator functions makes a dramatic change with the next line, where I have the same formula as I had before concerning the total force of infection. Okay, now these are the time of reinfection of the case individual who is either initially susceptible or initially infected. And eta and I is the time of reinfection of the ith newly infected individual. Okay, and then of course the rate of new infections is given by this quantity. Okay, now of course I divide all those quantities by capital N, and I let capital N go to infinity. So what happens? This is the result. So we have an equation for G bar of t, the renormalized total susceptibility, and F bar of t, the renormalized total infectivity in the population time t. Notice that the second equation is not quite the same, because previously we had capital S bar of S, we have now G bar of S. But you see that, okay, here lambda enters, the random function lambda enters the second equation only through its mean. Only the mean of lambda and lambda 0 enter the equation. Here you have expectations. Of course, G bar of t, F bar of t are deterministic. The only thing which is random is gamma 0 and gamma. Okay? But you see that here the equation does not depend only upon the expectation of gamma, but some complicated expression of the expectation of gamma times some exponential. And this is due to those indicator functions. Okay? Because those exponential are just some conditional probabilities that you have not yet been reinfected. Those two exponential functions. Okay. Now we can combine we have already combined the exposed and infectious individuals into a unique compartment of infected individuals. Similarly, the susceptible and recovered individuals, we can put them in the same compartment. So we have a sort of SI model, okay? Because once you are recovered, R means S with gamma equals 0. R means that you are susceptible with susceptibility 0. Okay? So we have only two compartments, S and I. And then, and then the proportions of S and I obey these formulas. I mean, not equations. Once you have solved the equations for the two quantities J bar, F bar, you have explicit formulas for S bar, I bar. Okay? Okay, this I have already discussed on the previous page. And now comparison with the models of Kermack-McKendrick. Okay, the model of Kermack-McKendrick is not so complicated as our model. As you can imagine, I mean, they were not probabilists. In the case of the SIRS model, with infection age, infectivity, and recovery rate, and varying susceptibility, our model in general is quite different because it involves not only the expectation of the random function gamma, but something more complicated. Now, in the particular case where gamma I of t is a given deterministic function, rho of t minus psi I, where psi I is the time of recovery, then our low-large numbers deterministic model coincides with the model of Kermack-McKendrick. Okay, so our model is an extension of the Kermack-McKendrick model. Now, the effect of waning immunity upon endemicity. Okay, there has been very recently a few other papers on the same topic, and now here I'm going to say something about not work to which I have contributed, but a work by Britton and Khalifi. They have compared progressive loss. They have compared progressive loss of immunity to the unrealistic behavior which is assumed in almost all models, where individuals jump instantaneously from full immunity to full susceptibility. By the way, their progressive loss of immunity is not a continuous loss of immunity, but they have jumps to various intermediate states between 0 and 1. Anyways, this is not too important, it's just technicality. Now, they show that with the same mean susceptibility, progressive loss of immunity induces a more severe endemic situation and requires higher vaccination coverage to avoid an endemic situation. So again, like in the question of extinction of an epidemic, the use of simplified models may lead the authorities to decide measures which are not enough severe to be really efficient. So, so the use, I have shown you several models which are certainly more tricky, more complicated than the usual OD models. I strongly believe that they are more realistic. The question is, do we want to use more realistic, complicated models, or do we want to use simplified models? Okay, if we use simplified models, we should be aware of which bias it will induce on the final result or decision. And this is the kind of information which is important. Okay, let me give you some references. So this is a paper of Chevalier that we inspired us. So this is a paper on the COVID, which I showed you a picture about this. These are the two papers on epidemic model with varying effectivity, which appeared in 21 and 22. The first one with a stronger assumption than what I've stated, and this one with exactly the assumption I gave in my talk on the lambda. And this is a paper with varying infectivity and susceptibility, which has been submitted quite some time ago, but no answer so far. Okay, I am happy to quote, Foutel, Rodier, Charpentier, Guérin have also worked, oops, sorry, there is a misprint here. It's not said in their title, but they also consider varying in susceptibility or waning in immunity, if you like. And I like to quote Foutel, Rodier because he has written a few papers in the last years, which are in the spirit rather close to what we have been doing in spirit. Always also non-Markov model, etc. This is the fundamental paper of Kemak-McKendrick to 1927, and then there are two papers later. This is the paper by Britton and Khalifi I was quoting in the last slide. And finally, this is the paper with the PD model, which I've shown on one slide. Okay, thank you so much for your attention.
Thank you, Etienne. So, questions?
Thank you so much for the talk. I was just curious about the Volterra equation you show us. It seems they are nonlinear, right? Because of it's not convolution linear Volterra equations, they are nonlinear. And yes. Could you say something about their long time behavior?
No. I've not studied this question, so I mean in the SIR case, there is nothing interesting to say about the long time behavior, because sooner or later, if there is no flux of new susceptibles, sooner or later the thing will stop. Okay. Now, in the case of the SIRS model, I mean the work with that work, then we have some results of our large time behavior. And okay, I don't know what I should say in a minute, but so we have conditions under which there is an endemic situation, etc. But it's, I mean, we are not completely happy with the results we have obtained. I mean, so when you have ODEs, large time behavior and infinite time behavior, is rather easy to describe. In the case of Volterra equation, it's much more tricky.
Thank you.
Any other question, remark, comment? If not, let's thank Etienne encore une fois.